Steve, welcome back. We are obviously still in a remote situation, but you wanted to tell us a bit more about how that, how this kind of connection's working.
Yeah, I mean, I thought it'd be interesting. I mean, obviously we've talked about remote working, but I mean, obviously a lot of the things we're doing is we're using video conferencing or voice over IP type software to have conversations with people, not just in a business context, but also with friends and family. I mean, I've lost track of the number of Zoom calls or FaceTime calls to support Dave that I've had to make in the past 8 weeks or however long we've been in lockdown. I lose track. So I thought it'd be interesting to sort of talk about the technology that's involved there, because as Steve Jobs put it when he announced the iPhone 4 and talked about FaceTime, the technology required to do it is a bit of an alphabet soup of technologies that you need to go through. So what I thought we could do is just spend some time going over how video conferencing works. The first thing to say is this is going to be an overview of what's involved. We'll come back probably and do some more in-depth videos at little bits, but this one's going to give the big picture and then we can zoom in later on to talk about that. We're also going to keep things simple, so let's simplify this problem down to the sort of conversation we're having now, which is one person talking to another person. We'll come back and talk about how we have multiple people, but I'm sure you can guess how we can do it. You just have multiple connections between the different people to do it. And we'll only consider it going in one direction from me to Sean or from Sean to me, because the other direction is basically the same in reverse. So we'll simplify it right down so we can have a discussion about what's involved in getting the voice and pictures from my end to get to Sean, what we would call perhaps mouth to ear. How do we get the voice from my mouth to Sean's ear across all the networks involved? What's actually involved in setting those things up?
You're breaking up there, Steve. Say that again. I'm joking.
yeah.
Okay, so you mentioned there the sound and me hearing what you're saying, but obviously we've got a video element to this as well, important for YouTube as much as anything. But we're going to talk about how the video connection works as well.
Yeah, we'll talk about video as well. But I think the important thing actually when you're having these conversations is that, bizarrely, even on a video conference, the audio is more important to following the conversation and having a sort of natural conversation between the two people. If the audio goes wrong, then you can't hear what's being said, or the conversation becomes a jumbled mess. So actually, even when video is involved, the video signal can break up, or we can drop the quality on it a lot easier than the audio signal. If the audio signal starts to break up, then the conversation, the flow of it will break down. People will start talking over each other. They won't be able to follow what's being said. So we'll start off looking at the audio, and then we'll talk, after we've done that, about how we put video alongside that. Because actually, once you understand how the audio works, the video signal's going in a very similar way, with a very similar set of problems, and you just have to send video rather than sending audio data across the network.
When you rang me this morning, as well as my computer starting to bleep to tell me that you were trying to connect, also my phone's going. How does that segment of it work? How do we know that we want to make a call?
So there's really two things that are involved with video conferencing. There's the call setup, which is sort of making sure that Sean knows I want to speak to him and that he accepts the call. And then we also need to establish how we actually send data between the two of us. And there's also actually sending the data over the connection, so taking the audio and the video that we want to send and actually sending them over the internet. And I think it's easier to talk about how we send the data first, and then we'll look at how we do call setup and what's involved in that in another video, because that actually involves making sure that we can get the data to each other, and so we need to know how the data is sent, so we know the problems that are involved with sending the data. Talking about how we transfer the data, there's loads of things that are involved in this. It may seem like a simple thing to just take a piece of audio and send it over a network, but actually when you think about what's involved in making this into a conversation and not just a live stream, because in the live stream I'm just sending data to Sean or whoever's watching, and they're enjoying whatever it is, insert your favorite type of YouTube live stream here. But with a voice over IP or a video conference, we're having a conversation. And so we need to make sure that the connection we've got enables the conversation to happen as if the technology wasn't there. We don't want the technology to get in the way of what we're doing. And so we need to think about things like, how much bandwidth is this going to take? I mean, we've all got network connections, but they have a finite amount of data that we can send. I mean, in an ideal world, we wouldn't worry about it. We could just send all the data coming from the microphone, coming from the camera, straight down the network, and it would appear at Sean's, and everything would just get there, and it would work.
So basically what we're saying is that we need to shrink that down before it goes through our connection so that we're not sending too much data and clogging it up and causing latency, right?
Yeah, so I mean, we've got oodles of data coming in the video. I mean, the audio for recording sort of CD quality audio is about 768 kilobits per second. So we've got a lot of data going down. And okay, a modern network connection, my home network's 300 megabits down, 35 megabits up, a gigabit symmetrical isn't unheard of these days in a home setting, but that's still a lot of data. And so obviously we need to sort of compress whatever we've got, or we need to make sure whatever we send fits within the bandwidth we've got available, because it's not just our bandwidth, it's your bandwidth as well. I've probably got a better internet connection than you.
You have. I know that you have. We've done tests in transferring material back and forth that proves that. But yeah, the point is, I suppose, there's even more considerations. You might live in a household with 4 or 5 people, someone who's streaming a movie at the same time, someone else who's trying to make their own call. So yeah, there are all sorts of considerations, aren't there?
Yes, so there's lots of things that affect the bandwidth. Is who else in the house is using it. There's what you've got, what I've got. There's what's involved in the network between it. If the network gets congested, then the bandwidth will drop, even though each end is technically capable of sending that. So we need to take that into account. So the bandwidth is important because we need to make sure that we can actually send the data, that we're not trying to force too much down the pipe, as it were, to the other end. What also is important is the latency, or the time it takes from me saying something coming out of my mouth to Sean hearing it through his ear, or what's known as the mouth-to-ear time. So the mouth-to-ear time, or the latency of the connection, is one of the key issues that we need to minimise. The telecoms industry found many years ago that actually, as long as it's below 100 milliseconds, the conversation will flow naturally. People will be able to have a conversation as if it's not there. So we want to try and minimise that as much as possible. If it goes above 100 milliseconds, then the conversation starts to break down, because I think you finish speaking, I start speaking, but because of the delay, you think I'm not going to say anything and start saying something, and we start talking over each other, then we stop, and then we both start speaking again at the same time, and as it goes on. And very quickly, once the latency goes above 100 milliseconds, the conversation will sort of break down into a, Sean, do you copy? Over.
Yes, receiving, over.
Good. Out. We want to make sure whatever we do, we minimise the latency. So the network itself has some inherent latency in it. You can measure that by running the ping command on your computer and seeing how long it takes to get from your computer to another and back, and then halve it. And that shows you the latency on that network connection. But this is also related to bandwidth, but not directly. If your bandwidth increases, your latency will go down, but it can also go up. And the other thing to bear in mind is that you're never going to get away with zero latency. And actually, we expect latency in a conversation. So as we sit 2 meters apart, as we're all socially distanced, there's a natural delay as the sound waves propagate from my mouth to someone's ear. So there's always latency in the conversation. What we want to ensure is that whatever we do doesn't introduce any more latency. And some of the things we might do to, say, preserve bandwidth are going to increase latency. And so we want to balance what we do there with what we do to maintain latency. So it might actually be better to use more bandwidth and have less latency, or to go for a slightly worse compression and have a sort of algorithm that compresses not as well as it could to reduce latency. You want to sort of try and keep the latency down as low as possible. The other thing you want to take into account is AV sync. So we want to make sure that the words coming out of my mouth are in sync with the pictures, as they aren't at the moment, because when that happens, it becomes really hard to follow what's going on. It looks odd. So we want to also try and maintain sync between what I'm saying and the video. And of course, because they're going to go through different routes, because we're going to compress the video in a different way to the way we compress the audio, we've got to be able to pair them up back at the other end so that they appear in sync. And again, that will affect latency, because if it takes longer to compress the video than it does to send the audio, then we have to delay one at the other end so that we can match them. So latency is a really important thing in a video conferencing. We want to try and minimize that as possible. And lots of the things that happen are involved in minimizing the latency of the connection. Other things you need to take care on is that if you think about the way this call is working, I'm speaking to Sean, it's coming out of his loudspeaker or through his earpiece in my case, and in Sean's case. But if that's coming through a speaker, that will get picked up again via the microphone. As I speak to Sean, I will get an echo as it comes back. which makes the conversation really the thing. So another thing you end up having to do, and we won't go into this in any detail in this video, is either suppressing the echo by sort of muting one end of the conversation when that person's speaking, or you can create circuits which cancel the echo by sort of taking the signal that's coming in and feeding it back and sort of in antiphase to sort of cancel out what's going on there. And there's lots of maths involved in that, but that's a story for someone else in another video to cover. So we have to take all these things into account, and of course as the latency increases, the echo will get more noticeable and certain things. In fact, there's one networking standard where its packet size was created purely on the amount of time that you could get from one end of France to the other without needing echo cancelling, so they went for 53 bytes or something, but that's another story. ATM's a complete other networking topic that we'll talk about at some point. So we've got to maintain bandwidth. We need to make sure we fit within what's available on the network, or less if other people are using it. And again, that can change. You might start a conversation and then someone starts watching Netflix on the same network connection, or the network may get congested elsewhere in the path between you and the other person as lots of people on the same ISP start watching the latest cat video on YouTube or whatever it is people do on YouTube. The latest Computerphile video, of course, it's far more interesting than cats. We have mice. So these things will change. We need to match that in our system. But we also need to keep the latency down, and we need to maintain AV sync. So how do we go about building a system? Let's start drawing a diagram of the bits that are involved. We're going to talk about how we can get the voice from me here to Sean over there. So at Sean's end, we have something that looks a bit like an ear. And over at my things, we have something that looks a bit like two lips. This has changed colour. And we're now going to talk about how we can send a signal from there to there. If we just start building this up as we go, the easiest way is that we'd have some sort of microphone at this end, and we'd have a loudspeaker at Sean's end, and then we could just connect a wire between the two, and as I speak, the microphone converts my voice into an audio signal, an electrical signal that represents the same waveform as my voice, sends it down the cable, and that at the other end, the loudspeaker converts that back into sound pressure waves that Sean then hears. This is your standard plain old telephone system. It's exactly how that worked, except the cable was sort of controlled by switches, but effectively once it was set up you had a connection between the two. But we're talking about sending this over computers, so we're going to end up having to send this digitally. So what we're going to end up doing is taking the signal out of the microphone, and then we're going to run that through an A to D converter, and what we get out the other end is a series of bytes that will represent that audio signal. It's a mono signal, so we'll get a single stream of bytes that represent that. And we can adjust the quality here by choosing the sample rate and how many bits we use to represent the audio. So we could go for sort of CD quality sound or better, which would give us a lot of data to send, or we could sort of do what the phone companies originally did, was only sample it at 8 kilohertz, which is 2 times 4 kilohertz, which is the highest frequency you normally get in a voice signal, and so you capture all the data required for voice and you don't send anything else, and you use 8 bits, which gives you 64,000 bits per second. So that's going to give us a set of data bytes, and they're going to come every 8,000th of a second. Let's just go with that to keep the numbers simple. So every 8,000th of a second we're going to get another byte of data representing my voice. And so that's going to come out as a chain. And at the other end, again, we have the opposite, so we'll have a D to A converter, digital to analog, which regenerates the analog signal, which can drive the loudspeaker. And we can then send this across, and it would all work. We've digitized it, but we still need that cable in there. So what do? Well, we need to send this over our network. Our network, the internet, is packet-based. There's been a long debate between telecoms people. Do you go for sort of circuit switch networks, or do you go for datagram packet-based networks where you just put things in a packet and send it like you're sending a letter to the right person? Packets seem to have won out. Sort of circuit switch ones like ATM and so on seem to have pretty much died out, or used to send packets over them anyway. So we're going to build them up into packets. But now we've got an interesting problem. We've got data coming every 8,000th of a second from the A to D converter, and we need to put them into a packet. So if we just go for, say, 1,000 samples, that would be 1/8 of a second at 8,000 kilohertz sampling rates. That's over 100 milliseconds there. So we probably want to choose a smaller packet size. So as soon as we start building these things up into a packet, we've got to wait for the right number of bytes to come in before we can send the packet out. That's going to introduce some latency. So we need to make sure we choose a packet size that is small enough to not introduce too much latency. So let's say we just had 1 byte in each packet. Well, we could send that over. That would mean we didn't have any latency, but we then have a situation where we'd be wasting bandwidth because that 1 byte would have several bytes of packet headers on there for the sort of IP header and so on that you would need to send it across. So that'd be very wasteful. So you want some there. And so you need to choose the right number of bytes to make this sort of fit there. So if you make it too many, then you'll use your bandwidth better, but you'll increase your latency. So you have to sort of rob Peter to pay Paul that to find the right thing. And of course, as the network changes, those conditions will change. So you may have to change that as the thing's going on there. So we're suddenly going to get a delay here by building things into a packet. And then you get that packet at the other end, and you take the bytes out of that one by one and feed them to your D2A converter. There's still an issue here as we send that over the network. You're taking the data in the packet and you're reading out the bytes one by one, sending them to your DA converter every 8,000th of a second. So we can send that. But when you come to the end of the packet, you need to make sure that you've got the next packet with the next set of bytes there at the next 1/8,000th of a second later. If it comes later than that, you haven't got the data, so you can't send it out to the DA converter. What do? Well, you end up having to play silence or whatever. So we need it there 1/8,000th of a second. But if you backtrack to my end of the connection, to send that, I can only send that when the network conditions are clear. So if I'm sending another packet, let's say I've got a 1500 byte packet from a network transfer where I'm sending this video to you, Sean, at the same time, that's just started, that's going to take some time to send. I can't send my packet of data with the audio connection until that's finished sending, which will delay it a bit more, and then which will delay it at the other end. So actually, although we've got the packets there, we're going to end up with some sort of buffering after that, just because of the network will be being used for other things. And actually every step along the network is going to introduce some buffering as well. That means that at your end, there's a very good chance that you haven't got the data you need to feed to your DA converter when you finish going through that packet. So we need to put something in place to make that work. And the way we can do that, typically, say in a live stream thing, is that we put a buffer here and we just start buffering or queuing up those packets. So we know we've got 2 or 3 in memory all the time, so that if the one arrives late, it goes on the end of the queue, and then by the time we come to it, we've got to that point. But that introduces more delay. So we're going to need to make sure that the buffer there is as small as possible, perhaps 2 or 3 packets, and that packet size is small enough so that we don't notice that additional latency we introduce there. But there's another issue here, and if you think back to the video we did on VPN, we talked about how there's 2 ways we can send data over the network. We can either say use a TCP connection, which tries to emulate a stream between the 2 connections where we send every byte down there and it arrives at the other end, guaranteed, one after the other in the order they're sent. Now you might think that's great, that's exactly what we want for an audio conversation. We want all the data to get there so that you can hear everything I said. But if you remember, the way we said that does that is that TCP, if it doesn't receive something, will wait and then ask for it to be sent again, and then it'll send it again. And if that happens, that's going to delay that packet arriving, and because it's guaranteed everything is happening in order after that, every other byte will be delayed by that point. And so the latency will increase, and as packets will get lost on the internet, because it's the best effort network, it's guaranteed to lose packets, then we'll be getting packets lost and lost and lost. And so the latency over the conversation will creep up and up and up imperceptibly, but eventually by the end it could have got to a point where you can notice it. So TCP actually perhaps isn't as good an idea for sending this as you think. The alternative way we can send that is say just to send the packets out there and let the computer do its best to get there. And if they get lost, they get lost. And actually it turns out that, certainly for audio and also for video, this isn't as much of a problem as you might expect. Because if you think about it, if our packet size is small enough, let's say we're sending 80 bytes, that's 1/100th of a second. If there's a 1/100th of a second dropout where the packet gets lost on the audio, you're probably not going to hear it. You'll be able to pick up the sort of conversation as things are going, and the next packet will come along, and so all you'll get is a sort of small bit of silence as you're hearing this bit now. And actually that's quite natural to us, because as we're having conversations, there are other sounds that we hear which might cover up bits of the conversation, and so we're used to those sort of things. So actually, it's better to have packets go missing and then just carry on and deal with what we've got and deal with that, than to actually try and guarantee everything's going there. So when we send these things out, we want to send them using UDP rather than TCP, because that enables packets to get lost. And as we said, we're not going to notice that in a conversation, whereas we would start to notice the build-up of latency as the TCP connection started delaying things, as everything got resent and resent and resent and resent and so on. So we use UDP. Now, rather than just stuffing the data into the UDP packet as is, we actually prepend to the data another header there, this time for what's called the real-time transport protocol. And this just gives us some details about what type of data is in this stream of packets. Is it audio, is it video, what codec is it using to compress things, and so on. But it also has a source identifier in there, so that we know that this is coming from the same stream. So it's sort of just a unique randomly generated ID for a stream that says these packets are all coming from the same source stream, the same audio stream or the same video stream. So you can sort of multiplex them and things. And we also have a sequence number in there, so we know whether packets have got lost or what order they need to go in, because the other thing we need to bear in mind is that the network might reorder things because they go different routes, in which case we want to reorder them ourselves back into the correct order, otherwise we'll get the audio jumbled up. And if we're buffering things, we get the opportunity to do this, or we can just drop the packets if they come out of order, and so on. But also we have a timestamp on there which tells us when this should be played, a sort of time that says either when it came from or when it should be played. And this is what we use later to synchronize the video to the audio. We stamp the audio with the time it came from, we stamp the video with the time it came from, and that tells us when the first byte in that packet should be played out. That works fine when the data rates are low. If, say, like with 64,000 bits per second, that's reasonable to send over a network connection even in the 1980s on something like ISDN. But if we want to do better quality audio, because that isn't that good quality audio, say we want to have CD quality audio, we're going to have significantly more data. We need to compress that down to a smaller size in some way so that we can send it over the network connection. And the way we do that is dead simple. We can just sit in between the A to D converter and the packetizing bits of the section and take that data and compress it, and at the other end, after you've read it out the packet, rather than sending it straight to the DA, which would sound horrible, you can sort of decompress it at that point. But again, compressing it, you're going to have to gather the data together, look at it, analyze it, and then decide how you're going to throw things away, because that's what compression is. It's working out, well, I can throw this information away and still recover the original signal, or something that sounds like or looks like the original signal. And again, when you decompress it, you're going to have the same sort of process at the other end. So you're going to end up introducing more delay and increase the latency at each end. So you've got to balance all these things to try and keep the latency as far below 100 milliseconds as you can, to try and keep the conversation as natural as possible as we're sending this across. The other thing we have to bear in mind is that this isn't going to be stable. Every packet we send is going to take a slightly different amount of time to send out. It's what's called jitter on the latency. We're not going to have a constant latency. If we had a constant latency, we could probably calculate that quite easily, but actually the latency will change as we're sending packets across there. As we said, someone might start using it to watch Netflix or the iPlayer or something. It might take a different route over the network. So one packet may take 2 milliseconds to get there, the next one might take 2.1, the next one might take 1.9, depending on various factors on the network. So you need to have the buffering in place to cope with these sort of things and things, and also to monitor it and adapt perhaps your compression rate. If things start to get more latent, you can compress it less, or when you've got more bandwidth, you can compress it more, so you've got smaller packets, so you've got more chance of going through, so on. Whatever's happening to try and maintain the call quality. But you want to keep the latency as low as possible as you're doing this. So that's how we do audio, and we can do the same in the opposite direction so that Sean can talk to me. And as I said, we need perhaps a bit of echo cancellation in there, which again is going to delay things a bit as we process that. It's really weird if you do start to hear delays on your own voice when having a conversation. If you start to play your own voice with it, even a sort of 10 millisecond delay, it will really change the way you speak.
You end up slowing yourself down as you hear the delay, and it's really strange.
So that's how we can send the audio. But what about video? Well, it works in pretty much the same way. We have a camera that captures our picture. That's going to capture 60 frames per second, 50 frames per second, 25 frames, even as low as 12 frames per second as we're sending the data across. And again, we're then going to need to compress that down because the video stream is likely to be, unless we've got a really fabulous bespoke video conferencing setup where we've got guaranteed bandwidth between the two things, HDSDI lines or whatever it is we've sort of laid down. We're going to have to compress, and even if you've got it, probably I'm going to still compress it down to a smaller size, and that's going to take time. And then we send that across, and we just send this across with timestamps, sequence numbers, and we can rebuild that at the other end to display on screen in the same way we do with the audio. One of the things we can do though, because we know the image isn't going to change that much in a typical video conferencing, the background behind me is static, the background behind Sean's static, so we can use interframe compression to throw bits of information away that doesn't change from frame to frame, so for example the background. But the way we normally do that is by working on a sequence of 15 frames, say, or 30 frames or 60 frames, and compressing them all in one go, which is going to introduce the delay. So we need to make sure that we design our codec that it doesn't introduce those delays. And you can start to do even more things like, for example, breaking the image down into sort of horizontal slices so that you can compress the top slice first, which if you're building the hardware from scratch, will often come from the sensor before the bottom half. If the machine's multi-threaded or got hardware support, we can be compressing one slice while we're sending the other over the network, so we can reduce the latency even more. And when it's received at the other end of the conversation, we can synchronize it with the audio using the timestamps in the RTP headers that tell us when this came from, and so we can match them up, delaying each of them as needed, so they can be played out in sync to whoever's watching the video conference, and the same can happen in reverse. We can now send the data over the network. We've got an RTP stream containing the audio, an RTP stream containing the video. They both have timestamps in them so that we can sort of synchronize them. The problem we've got, and this is because of how the internet's developed because there's too many people using it, is how we make sure that we know we're sending this to the right computer, particularly as they're likely to be hidden between network address translation and firewalls and so on. So in another video we'll look at how we set up the call and how we can make sure that my computer behind my network and my network address translation can talk to Sean's computer behind his router and his network address translation. And oh, wouldn't things be more simple if we just went to IPv6?
You only have to work out whether it's worth alerting the user if you find the key. So you download the temporary exposure key, you perform the encryption, you generate the potential RPIs and you compare them with the ones you've seen.
Or if you want a more slightly comprehensible message, it's saying maybe you haven't applied a function to enough arguments.